Oh, hello, folks. We're here to talk about conservation of matter. Last class, we actually did some investigation. We did a simulation where you investigated the reaction between hydrogen and oxygen to launch a rocket. Today, we're actually going to be looking at a little more in depth on what conservation of matter is. You should be following along with your notes. So here are the directions for your notes. Follow along with video assigned on Schoology. Hey, you're already on a video, so you're doing good. Take notes, read passages, and answer questions. So notice here that there is place for you to take notes. Okay, and then also questions embedded in here. There's passages where you should pause the video, read and answer those questions. Again, some more questions, some more notes. So a place where you can interact with your notes. Okay. Also, you have the ability of pause and rewind the video anytime to clarify ideas. You can also stop and ask me about things, right? So we're doing this in class, so you can actually ask me questions. An additional resource for you is your textbook. Here the pages are a textbook that corresponds to this material. It is also available on your virtual platform. You just need to go to Investigation 1, Experience 3. Okay, so you have lots of resources for you. All right, so let's begin the presentation. Conservation of matter. Learning objectives. Identify and describe how balanced chemical equations show a conservation of matter. Describe how mathematical representations of chemical reactions shows the number of atoms in unchanged between reactants and products. Okay. So let's talk about those things when time comes. We need to go way back, and before we talk about conservation of matter, we need to talk about what is matter. Okay. If you take any object and you start breaking the object into its smaller components, and you keep breaking it, and you keep breaking it, and you keep breaking it, you're gonna come up with obviously it's gonna get to a point where you're not gonna be able to see it. Okay? But if you could break it into its smaller components, you would finally find yourself in front of an atom. Okay, an atom is very tiny. You never would be able to just see one atom, but pretend that you can see it. We have several models of atom. This is one type of model, and we usually use this in high school to teach high school chemistry. But if you went ahead and you took college level chemistries, you would find out that there's several different types of models. But this is called a Bohr model. And in a Bohr model, atom is made out of three things. Okay. Electrons, which circle around the orbital. Protons and neutrons, they're right in the nucleus. Okay. What's relevant to us here is that the atom's mass is in the nucleus. So electrons does not have a lot of mass. Most of the mass of an atom is inside of a nucleus. Okay, so that's the idea here. Okay, a few other notes about matter. Matter occupies space and has mass. Like energy, matter flows through systems. Unlike energy, matter can be directly measured. So if you remember your calorimetry experiment where you were not able to measure heat directly. Instead, what you did, you measure how much heat, how much energy affected the water, right? So you measured the water, you were not able to measure the heat directly. That is not the case with matter. Matter, we measure things directly. For example, if I want to know the temperature of a water, I can just stick a thermometer in there and measure the temperature. If I want to know the mass of water, I can just put it on a scale, right? So matter we can measure directly, not energy. Matter cannot be created or destroyed. We talked about this before. Some very common misconceptions are it does not disappear. Matter cannot disappear. It does not become energy. That's a very, very common one when people think it becomes energy. And there is a note in here in most cases. And the last slide I'll talk about one that is not the case. And it does not get destroyed. Okay, so those are important things. It might seem very obvious right now, but when you look at a chemical equation, that is our way of showing matter and changes in matter, all of a sudden all of this kind of falls apart. Okay, that's why I'm starting to state here. For example, and this is when it begins to fall apart, you put a massive amount of wood in a fire, like large amount of wood in a fire, and then in the morning you go back and there's small amounts of ash. Okay, where did all that mass go? Right? So you might think it might have become energy, which would be a wrong thing to think. You might think it just disappeared, which again is a wrong thing to think. So we need to start thinking about what happens to matter. Okay, what happens to matter during a chemical reaction? Okay, to kind of illustrate this point, I'm gonna play a video for you. Okay, and there is a place that you need to record a couple pieces of information, and I'll give you a heads up where you need to record. But under your notes, there will be a part that says baking soda and vinegar. Okay, so make sure that you go there. All right, folks, make sure that you record 35.0, and that's your reactant. Ignore that little bit dripped. Okay. And make sure you record 34.2 grams as your product. All right, so then let's talk about how did it go from 35 grams to 34.2, I think, 34.2 grams. Where did the mass go? Right, so that's one of your questions that you need to answer is what happened to the mass? It didn't disappear, it didn't get destroyed. Okay. The key to this answer is to understand that one of the products, you should have noticed a fizzing happening, right? So one of your products was a gas. Okay. And what we know about gases is that occupy any space that it's allowed to occupy. It just diffuses. Okay, so there was nothing preventing the gas from staying on the scale. Okay, so the mass that was lost, it was because the gas that was part of the product evaporated, not evaporated, but actually dissipated. It left it, right? So one of the products disappeared, not disappeared, sorry, I shouldn't say disappeared. One of the products left the balance. How about that? And that brings us to a very important point. Open and closed systems. Okay, and we talked about this before. but we didn't talk in a context of mass. Let's go back and talk about in a context of energy. So the red arrows are here representing energy or heat. Okay, so you have, let's call this a glass of cold water, okay, very cold water. And it's just a regular glass. And if you live on a counter, the heat or the energy from the surroundings is going to go towards the glass, and eventually the glass of water is going to get warm. So heat is going to come towards all the directions. Okay. If you take the same glass of cold water and you put a lid on it, it still won't prevent energy from flowing through the system. Okay. So that lid is not going to do anything to prevent energy from leaving or from coming into the system. However, if you put this glass of water, of cold water, in an insulated container where there's no interaction between the system and the surroundings, then you're allowed to keep the water cold for a long period of time. I must say that insulated containers are usually not 100%. There's always some leaks here and there, but ideally, an insulated container prevents the system from interacting with the surroundings. All right, let's go through the same exercise, but now thinking of matter. Okay. You have a container just like before, and it's open. If the matter happens to be gas, it is gonna leave. Okay. Even if it's a liquid, right? If you have a glass of water and you allow that water to sit long enough, the water molecules are going to evaporate. So it's able to leave the system. However, if you put a lid on it, you prevent mass from leaving it because mass cannot go through mass. Okay, so matter cannot go through matter. That's the idea. Okay, so you're able to keep matter inside if you just put a lid on it. Okay, in here, the insulated container will do just the same thing as this one, okay? It's gonna do the same thing. So back to the experiment, which I will run again, if there was something that could hold on to the gas in here, so make that into a closed-in system or matter, you would not see any change in mass. Okay? If you were able to trap the gas that was released here, you would not see any change in matter. Okay? So take a moment, pause here. There are a couple questions, I believe, for you to answer in your notes. So take a pause and answer those questions and then come back to the video. Okay, so there's a label here. So this is an open system, this is a closed system, this is an isolated system when it comes to matter. All right, so we need to talk a little bit now about chemical reactions. So this is how we measure the flow of mass. So the symbols here, the K, the Cl, the K and Cl represents atoms. In this case, they're specific elements. K represents potassium, Cl represents chlorine, and then KCl is the combination of potassium and chlorine is potassium chloride. Here are the reactants, right, before the arrow. Here the product. We call the numbers in front, we call them coefficients, and it just says how many of each atom is present. The little number over here is a subscript and is applied when two or more atoms are bonded together. Okay, it's just another way to say there are two chlorines, but they're bonded together. Okay. So in terms of conservation of matter, this is what you need to know. You don't need to know that K is potassium or Cl is chlorine. That's, I believe, is unit 3. Okay, eventually you will need to know, but not for this one. What you need to know here is that mass is conserved during a chemical reaction. How? Well, potassium is here and potassium is here. So potassium was before the reaction, potassium stay after the reaction. Chlorine was before the reaction and stays after the reaction. And the amount of them is also the same. 2 potassiums, 2 potassiums, 2 chlorines, 2 chlorines, because the 2 here distributes to both. Okay, so 2 and 2. So not only the elements or the atoms need to be the same, the number of them needs to be the same, and we call this a balanced equation. Okay, so remember in a objective it says balanced equation, so this is a balanced equation. They're correct on both sides. There's the same number of atoms on both sides. Okay, here's a video explaining another type of chemical reaction.
Let's talk a little bit about chemical reactions. And chemical reactions are a very big deal. Without chemical reactions, you or I would not exist. In your body right now, there are countless chemical reactions going on every second. Without chemical reactions, we would have no life. We would not even have the universe as we know it. So what are chemical reactions? Well, they're any time that you have bonds being formed or broken between atoms or molecules. So what are we talking about there? Well, this is maybe one of the most fundamental chemical reactions. Once again, if this one never occurred, we'd be in trouble. We would not have any water. But let's think about what it is actually describing. So over here on the left-hand side, we have the reactants. Let me write that down. So here we have the reactants. These are the molecules that are going to react, and then we have an arrow that moves us to the product. Let me do that in a different color. So we have an arrow that moves us to the product, or we could say the products. And so what are the reactants here? Well, we have molecular hydrogen and we have molecular oxygen. Now, why did I say molecular hydrogen? Because molecular hydrogen, which is the state that you would typically find hydrogen in if you just have it by itself, is actually made up of 2 hydrogen atoms. You see it right over here. 1, 2 hydrogen atoms. And what we have, in order to have this reaction, you don't just need 1 molecular hydrogen and one molecule of hydrogen, 1 molecule of oxygen. For this reaction to happen, you actually have 2 molecules of molecular hydrogen. So this is actually made up of 4 hydrogen atoms. So let me make this clear. So this right over here, this is 2 molecules of molecular hydrogen, and that's why we have the 2 right out front of the H sub 2. This little subscript 2 tells us there's 2 of the hydrogen atoms in this molecule, and then this big white 2 that we have right over here, that tells us that we're dealing with 2 of those molecules for this reaction to happen, that we need 2 of these molecules for every molecule of molecular oxygen. And molecular oxygen, once again, this is composed of 2 oxygen atoms. 1, 2. So under the right conditions, so you need a little bit of energy to make this happen. If under the right conditions, these 2 things are going to react, and actually it's very, very reactive, molecular hydrogen, molecular oxygen, so much so that it's actually used for rocket fuel, you are going to produce 2 molecules of water. We see that right over here. And look, I did not create or destroy any atoms. I had one oxygen atom here. It was part of the oxygen molecule right here. And then I have the second one right over here now. Now they are part of separate molecules. I had 1, 2, 3, 4 hydrogens. I now have 1, 2, 3, 4 hydrogens, just like that. And actually this produces so we could say some energy, and I'm being inexact right over here. Some energy. And then we could say a lot of energy. A lot of energy. So this is a reaction that you just give it a little bit of a kickstart and it really wants to happen. A lot of energy. So one thing that you might wonder, and this is something that I first wondered when I learned about reactions, well, how does this happen? Is this a very organized thing? Do these molecules somehow know to react with each other? And the answer is no. Chemistry is an incredibly messy thing. You have these things bouncing around. They have energy. They're bouncing around all over the place. And actually, when you provide energy, they're going to bounce around even more rigorously enough so that they collide in the right way ways so that they break their old bonds and then they form these new bonds. So whenever you see these reactions in biology or chemistry class, keep that in mind. It looks all neat and organized, but in a real system, these are all of these things just bouncing around in all different crazy ways. And that's why energy is an important thing here, because the more energy you apply to the system, the more that they're going to bounce around, the more that they're going to interact with each other. The more reactants you put in, the more chance that they're going to bounce around and be able to react with each other. Now, I'm going to introduce another word that you're going to see in chemistry a lot. This water, these two, we have two water molecules here. We could call them molecules, but since they are actually made up of two or more different elements, we could also call this a compound. So water is, you could call it a molecule, or you could call it a compound. So this is a molecule or compound, while this molecular hydrogen, you would not call this a compound. And this molecular oxygen, of course, it's a molecule, but you would not call it a compound either. And just to get an appreciation of how much energy this produces, let me show you this picture right over here. That's the space shuttle. And this big tank right over here, this big tank contains a bunch of liquid oxygen and hydrogen. And to create this incredible amount of energy, it actually just you mix the two together with a little bit of energy, and then you produce a ton of energy that makes the rocket, that makes the space shuttle. Well, the space shuttle's been discontinued now, but back when they did it to make it get its necessary velocity.
All right. So, on your lab where you did the conservation of mass, you launched rockets, right, using different combinations of oxygen and hydrogen. That was the example that from Khan Academy that they were using before. And the interesting thing is that the energy that's released is released to launch the rocket. And the way this is done is so the product is water, and we know the water becomes gas or vapor very easily. But the heat is so intense and happens at once, the water molecules begin to expand so quickly that this occurs almost like an explosion, because there's large amounts of heat being generated and is being applied on a gas. And when the gas expands, it expands so fast that actually causes the rocket to move ahead, to move towards the sky. This was the results from your lab right after you did test 1, 2, and 3. And I just want to point out, and again, back to the Khan Academy video. So you have oxygen and hydrogen, just like the reaction before. And the product is water, right? And we began here with 8 milligrams of oxygen and 1 milligram of hydrogen. And notice here that 8 plus 1 equals 9, right? So those two things combined created 9 grams of water. Notice that there was no oxygen and no hydrogen left behind, right? So this is the reactant and this is the product. This was not enough fuel, even though it produced energy, it wasn't enough energy. Again, a rocket is very heavy, it requires a large amount of energy to propel it. In a second test, you doubled the amount of oxygen, and they're following a very fixed ratio of 8 to 1, right? So you also doubled the amount of hydrogen, and you produced double the amount of water, right? And you were able to, the rocket was able to launch, not very far, but it actually was able to go up. And then here is 5 times the original amount, and then here is 5 times the original amount, and guess what? You're going to get 5 times the amount of product, right? So energy is being conserved throughout a chemical reaction, and obviously you got way more energy able to do the work. One of the extent questions gave you a wrong ratio of not 8 to 1, but for example, if I have 8 here, instead of 1, I had 2, the outcome of the reaction would be the same because it requires an 8 to 1 ratio to produce the amount of water. So you would just have some hydrogen left behind, but it requires both in order for the reaction to take place. I hope that makes sense. I also want to show you another example of combustion. There's this really cool video because now that we understand how combustion is able to mass is able to be conserved in a combustion reaction, we need to know how does it do work.
Combustion works. An internal combustion engine converts the energy of combustion into useful work that can cause a vehicle to move. One cylinder of a 4-stroke internal combustion engine is shown here. In an internal combustion engine, gasoline is combusted. Gasoline contains many different hydrocarbons, including liquid ethanol. When ethanol is ignited in the presence of oxygen, a large volume of gas is produced, which forcefully expands. This expansion enables the engine to do work. Each ethanol molecule must react with 3 oxygen molecules in the air-fuel mixture in order to react fully. Even though the combustion reaction is explosive, generates a large amount of heat, and dramatically changes the appearance of the reactants, no atoms are gained or lost during the reaction. Mass is conserved in the reaction. In the intake phase of the engine cycle, a mixture of air and fuel is drawn into the cylinder. The piston lowers and the crankshaft turns 180 degrees. In the compression phase, the air-fuel mixture is compressed. The piston is raised and the crankshaft turns 180 degrees. In the combustion or power phase, the spark plug ignites the fuel and air mixture, causing a combustion reaction. The volume of gases produced in the reaction forcefully pushes the piston down, turning the crankshaft. In the combustion of ethanol, for every molecule of liquid ethanol that reacts with 3 molecules of oxygen gas, 2 molecules of carbon dioxide gas, and 3 molecules of water vapor are produced. The heat produced in the reaction causes the carbon dioxide gas and water vapor to expand. This puts pressure on the piston, causing it to move. In the exhaust phase of the cycle, the piston returns to the upward position and the products of combustion are expelled. The ethanol combustion reaction is an example of the conservation of mass in chemical reactions. An internal combustion engine is an example of how chemical reactions can be used to convert energy stored in chemical bonds into useful work. Key takeaways. To summarize, mass is conserved during combustion. The combustion reaction releases energy. The energy released in a reaction can be used to do work.
All right. There we go. All right, so when we're talking about combustion, we have what we call a complete versus incomplete combustion. So we talked about this before, but combustion requires fuel, it requires oxygen, right? And it requires an ignition source. In the case of the internal engine was the spark plug, I believe that's the name of the ignition source for internal engine. Okay. The product are carbon dioxide, water, and lots of heat. Okay, and that heat is used to do work, right? So to get the car to move, to get the car to different parts of the car to operate. However, combustions are not always ideal like that. Sometimes we have what we call incomplete combustion, and it's usually due to low levels of oxygen. And if your car is kind of old, that usually falls in that incomplete combustion. The thing with incomplete combustion is that it generates a lot of carbon monoxide, which is highly toxic. It also generates way less heat. It generates way more water, and generates other gases that are pretty toxic as well. You usually see this if you have a campfire and the fire is going out. You start seeing that smoldering phase where there's a lot of water vapor, and it's kind of getting reddish, almost like they have it here, kind of reddish red, reddish flame. It's where it comes towards an incomplete combustion. Okay, just to give you an idea that combustion is not this very cookie cutter way that we described in chemistry. Okay, so this slide you do not have in your notes, and actually is a side note. It's more like a side note. I'll never ask you anything in terms of quizzes about this, but there are cases where mass is not conserved. And who discovered this was Einstein when he developed the formula of E equals mc squared. He was able to show at very, very unique conditions, you're actually able to make mass becomes energy and vice versa. And that's wild. I mean, stars do that all the time, but we eventually were able to do it ourselves through nuclear reactions, through fusion and fission. Okay, so I won't go through a lot of nuclear chemistry in here, but if you're interested, your textbook talks way more about this. Again, it's a side note. This is the end of the presentation. I just want to point you to the end of the notes. Okay, so we talked about conservation of matter during combustion. Okay, and then the second part, which says claim, evidence, and reasoning. Okay, that part you are doing on your own. Okay, meaning without any video. Please read the scenario, and you're going to be writing a claim, evidence, and reasoning. You're going to be looking for sources. You can also do some research online to gather evidence. Make sure that you follow the pattern that I went through with the previous videos on claim, evidence, and reasoning. Evidence needs to be data. Okay, and again, if you're doing this during class, you can ask me, is this data or not, right? And make sure that your reasoning can tie your claim with your evidence. So that is the end of the video. Please let me know if you have any questions.